Hello friends and welcome to a lecture on numerical methods. Today we will see what is Newton-Raphson's method for root of equation. This is Professor Arvind Prasad. So let's have a look. The equation that we have is 12x cubed minus 59x squared plus 79x minus 30. And if you plot the equation, well, the green line, I have just taken a small screenshot of it. The green line represents the trajectory of the equation. And of course, the curve of this particular equation meets the x-axis as 3 points. So these 3 points are nothing but the roots. So, well, you have the first root here, the second root here, and the third root here. Now, visually, one can see that, yes, one of the roots is 3, one of the roots is roughly maybe 1 point, somewhere around 1.2 to 1.2627, and the other one must be slightly above 0.666, near about 0.777. So 0 0.7, sorry, so 0.666 maybe. You really don't know. Let's have a closer look at it. Yes, so having a closer look at it says that yes, this is 0.666, this is 1.25, and this would be 3. Okay, so when we have such equations, how do we find? That is cubic equations. Now, one is well aware that once you have cubic equations and equations with the degree 4, 5, 6 polynomials, it's difficult to find the roots analytically. And then sometimes, most of the times, you have to resort to numerical methods to find the roots. Now, this is where Newton-Raphson's method really helps you out. So let's look at how do we use the Newton-Raphson's method and what is the idea behind it. So let's say we have this curve of y versus x. Now, you can take this curve, which I have shown you, just a zoomed up version of this particular curve near 0.3. Okay, so that's it. So how do we start? Well, first we take some estimate of where the root is going to be. So it could be on the either sides of the blue curve that we have. It could be here, it could be here. So we take a point which is here, that is towards the right hand side of the curve. And then we find the value of the equation at this point. To start with, we take a point x0 and we find the value of the equation at x0. So this is going to be fx0. Now at this very point, we draw a tangent. And that's going to be the derivative of the curve. The tangent is nothing but the derivative of the curve. And this tangent meets the x-axis here. So therefore, this is our next estimate of where the root would be. Of course, we keep estimating this way. So again at x1, we find out the value of the function. That is the equation that we had, cubic equation. And then we again draw a tangent there and we then estimate the second closest number, which is closest to the root, which of course gets closer and closer to the roots. Now, this appears to be working because, yes, with each new estimate, you seem to be getting closer to the root. Now, how do we write this mathematically out? So, the estimation is equal to the previous estimation minus fx over f dash x. Okay, so the xn plus 1th estimate of the root is equal to xnth estimate minus f at xn over f dash x at xn. Now, if we plug in our equations in this expression, what do we get? We get xn plus 1 is equal to xn. Now the numerator is of course the cubic equation that we had and the denominator is the differential of it. So we start with an initial estimate of one of the roots, that is the root which is 3. We make an initial estimate that is 3.2. This is a blind estimate. We really do not know what the roots are. So this is x1 is going to be, now the second estimate, the first estimate of the root is going to be 3.2 minus 11.856, which is nothing but plugging in the value of 3.2 in the numerator and then plugging in 3.2 in the denominator, we get 70.04. So the next estimate that we get is 3.03. Now after that, the further estimate is going to be 3. Now we stop here. Why? Because if we do any further estimates, we'll find that yes, the fresh estimates would be 3 itself. Okay, if you take 3 and you put it in the equation that you have, and the numerator is going to be 0. So that is the way we get it. 1 or 2, if you make a very good guess, okay, if your guess is fairly good enough and it's a very good guess near the root, 1 or 2 estimates should actually give you the root. Right? If, of course, you're away from the estimate, it should take you around 5 to 6 iterations of such kind to solve it. Now, let's find the other root. Now, this is pretty blind. I take an estimate of 0.8 and I do the calculation once again. I put 0.8 and get the numerator and get the denominator. The next estimate is 0.5926. Take that and again do the calculation, 0.6574. And then, of course, 0.6664. Now, here again, if I take 0.6664, I will not have any improvement in the root. That is because taking this will give you roughly equal to 0 on the numerator. So whenever you're reaching the root, remember one thing, the numerator values are going to be very, very small and there would be no further increments in the estimates. So that was all about how to use Newton's-Raphson's method to find out the root of any cubic. You can take any equation. This method, of course, does not apply to linear equations. So this is for any quadratic, cubic equation with the order 4, 5, 6, 7. Well, you may name the order and you get it, right? The only point here is that yes, one should know the function and one should take the derivative. The function goes on the top, the derivative goes at the bottom, and you have a minus in here. Take care, right? So that was the end of the lecture. A short but very simple and beautiful presentation of what is Newton-Raphson's method. Well, try it out. Take any equation, complicated equation with the order 4, 5, 6, and you'll be surprised. Yes, it quickly converges and gives you the roots. Well, that was all, friends. Goodbye. Have a great time. Have a great day and keep watching.